last time we talked about how if we were trying to find the slope of a function, in fact, let me get this other file open as well, 1 second. I showed you this image. Showed you this image last time, I believe. We talked about how if I'm trying to find the slope right here at, say, point A, that technically the way I do that is I create a secant slope to the left of A, like so. And I create a way to calculate that slope, which is nothing new. It's just the way you've always calculated slope. Then I create a secant slope to the right. And same thing. I create the formula for finding that slope. Then all I do is I make those secants shorter and shorter until they are infinitesimal in length. And once they are infinitesimal in length, I get this kind of a situation where it's like I zoomed in and the two secant slopes are becoming essentially identical. That's how you find the slope at a single point, how you find the tangent slope. Okay, any questions or curiosities coming to mind, just speak right up. Okay, so that's where we started last time. Today what we're doing is we are taking the work that others did. Basically what somebody did a long time ago is they applied that idea to several different types of functions. And when they applied that idea to several different types of functions, they came up with these shortcut rules. We don't get tested on where the rules come from in this class. We won't spend time showing you how you get from here to a rule. If you want to look it up online, you can find a lot of explanations, YouTube videos, etc. that will show you. But basically, we're just going to learn how to use the shortcuts. So for example, so the pink sheet that's in the sheet protector, that's your copy of these rules. They do have to be memorized before the next test. You will use them all year long. So even though they seem, every year people seem a little intimidated by how to memorize them. But you'll find that if you just do the homework and you use the notation I teach you to use, most of the rules will get memorized fairly easily, even though they look intimidating in the beginning. So don't let their appearance bother you. Just work little by little and you'll be okay. But they will have to get memorized. So for example, let's go, so you'll need your notebook today. The homework sheet that I passed out is not meant to be written on because there's not even close to enough space. So the homework sheet is the buff sheet. So don't do any writing on the buff. You just want to put your buff sheet in your notebook. I messed up and forgot to punch holes. So give me a second, I'll give you a new one. One moment, we'll replace your buff sheet with one with holes. I'll come pick up the other one here in a second, but here's a new one that's older, so you put it in the notebook. So you'll need to do your homework on paper for this homework, not on the buff sheet. Use separate paper for your homework. We're back to problems where notation is critical. So let me show you the rule here. Here's a better sheet with holes in it. Do that one in 1 second. So you're welcome. So here's the rule. That's why I'm going to keep setting things down. Pen. Okay, it really is important that you use proper notation with this unit. It's the only way you learn how to write in such a way that you get points on the written section. It also prevents a lot of mistakes. So here are the rules. You have to use the notation I show you. You cannot invent your own. I've had students in the past who create their own notation. It causes nothing but trouble. Don't do it. Don't say, I like writing it this way. It's wrong. The notation I show you is the notation you must use. As you get better and better, I'll help you learn how to write less. But again, you must use my notation. If you don't have my notation, you don't get to retake the test. It'll make more sense as we go along, so we'll just kind of dive in, but controls for the next class. Okay. So in your notebook, write down this. Just this, number 46. So the good news is the problems are easy to write down. They're very short. So just write that down. F of x equals quantity 3x to the fourth minus 5 squared. And the idea of this unit is that that's some function. What it looks like, I don't know exactly. I don't really care. But it's something, similar to this. Doesn't mean it looks like that necessarily, but it's something similar. And our goal is we have a formula here. This formula is how we find all the xy pairs of this function. So we could use that formula, we could plug in an x, and the formula would generate a y for us. Or we could do it the other way around. We could specify the y value and use some algebra to find the x value. Don't forget that's the purpose of that formula, find xy pairs. The goal of this unit, unit 2, is to come up with a completely new formula called f prime. I'm going to write that here. So we want to create the f prime formula. In the last unit, what we did was we would see a graph of f prime, then we'd have to use like Danica's chart to show how, what characteristics of f might be. For this unit, we're literally creating formulas. And the process of creating the formula ultimately does boil down to this idea of secant to the left, secant to the right, but the shortcuts make it a lot quicker. That's all. So we're kind of skipping the steps in between, which is how you get from secant slopes to a formula for a tangent slope. That isn't tested in our class. We're just going to go right to the shortcuts. Questions or curiosities so far? Awesome. Oh, before I forget to mention this, with the switch to the hybrid schedule, I don't know exactly how other classes will function. For AP, we don't have any choice. We have to stay on track for May 4th. So what you'll do is if you're not in class, you'll go to well, actually, even if you are in class, you're going to check Canvas each day. If you are here, you will have already gotten the homework assignment. You will have already seen the discussion. The video will be there if you need to see it again, plus extra resources. If you're not here, that's where you go. So you'll have to get the content via the video on the day you're not here. But I will be trying to post a lot of extra examples that you can also use to help you. We'll kind of go from there. But questions about the days you're not in class. So just go to Canvas. There'll be instructions for what you need to submit, homework, all that sort of thing. So anyway, here we go. So I want to get from F to F prime. The rules help me get there. So I've got to find the correct rule to use. Well, basically I just look down the list and I look at this function structure and I'm searching for the rule that will fit. So I look at my rule list, which is right here. It helps if I keep the window on the right screen. Hold on, I gotta move it over. Okay, so using the rules is really an exercise in identifying the type of function that we're dealing with. Here are the rules. And what I noticed right away is the problem that I'm working with fits the following pattern. Look right here. You have some function, I'm calling that function g of x, but it could be anything. Some function being raised to a number. That matches what I see here. I have some function right here. That function is being raised to a number. So in the rule, this is the g of x, the thing that's inside. F of x is the entire function, but for this particular case, the g is right here, that thing that's inside. You wouldn't need me to talk more about that. So now what you do is, using proper notation, we apply the rule. So I put the rule here just to help us so we don't have to flip back and forth so much. Just made a copy of it. Got a little bigger. So this symbol right here, d over dx of something, this is the derivative operator. It's saying apply, it literally means go find, so d means difference. So this is saying I want to find how much is the output value changing compared to the input value, because that's what slope is. Change in output divided by change in input. So this derivative operator is going to be applied to this function. So let's do that. So on your paper, you've already written this. You've written f of x equals. On the very next line, you're going to write d over dx of f of x. Like so. So write that down. I'll wait. Which is basically saying, don't write the next thing, just listen. I'm trying to find f of x represents the y-coordinate of this function. I'm trying to find how the y-coordinate changes, that's what d f of x means, divided by how the x-coordinate changes. That's a slope. I'm finding the slope of the function. That's why we have this notation here. Okay, questions? Cool, keep going. Well, we had an equation to start with. Here's our equation up here. We have to maintain equality. That's why I put in the notes here that if you don't learn to properly use the equal sign, you will not be allowed to retake the test, because you have to know how to use that properly to get points on the AP test. So back to here, that's got to equal something. Well, we apply the derivative operator to this half of the equation. Now we're going to apply the derivative operator to this half of the equation. That way we maintain the equality. We still have something equal to something. So you're going to write d over dx of this other half of the equation. 3x to the 4th, subtract 5, parenthesis squared, close parenthesis. So write that down. It literally is the same thing you've been doing for years, where you'll have an equation and you'll say, I'm going to multiply both sides of the equation by, say, 2. The only difference is what we're doing is we are applying this derivative operator to both sides of the equation. But still just algebra, just applying an operator to both sides. Curiosities or questions about anything? Okay? It will feel like in the beginning that it is taking a lot of writing, but with time you'll learn to skip steps. And it actually comes fairly quickly. But as we start out, yeah, you have to write a bit. So, next line. This line, we're not really going to do anything with it because that's what we're trying to figure out. The goal is to find how does the output, f of x, change with respect to the input, x. So write that style this time. Write that down. I wrote these two different styles because they test you on both kind of styles of notation. Those two things in yellow are exactly the same. They're just two different ways of writing the exact same thing. So I'll switch back and forth so you get accustomed to the variation so you aren't surprised on the AP test. Okay, cool. Now what we're going to do is take advantage of the shortcut. According to the power rule on your pink reference sheet, this type of expression is exactly equal to this expression. So I've already pointed out that the g of x is this. Here's my n. Now I just apply the rule. So n in this case is 2, so I write down a 2. That's right here, writing down the n. Now I'm going to write g of x. Here's my g of x, 3x to the 4th minus 5, so parenthesis. Now I need to go power of n minus 1. So it would be 2 subtract 1. Let's pull this out of the way a little bit. Now I have to write this expression, which is d over dx. I have the wrong thing. D over dx of the g of x. So I go d over dx of the g of x, which is right here again. I've learned from those who've been watching the videos online that I've got to be better at actually circling things. In class, I tend to just point. If you're watching the video, you can't tell what I'm pointing at, so I apologize for that. I'm trying to do a lot better at literally touching the board a lot more. Please.
You keep it the same as like the first part, and instead of doing d over dx, you you do D parentheses UX over DUX?
2 points for David. What he just said, let me just restate it. If I heard right, and just correct me if I'm wrong, David. Come on, pen. This one. He's saying, let's get this out of the way. Can I take this right here and use the other style of writing, which would make it look like this? Is that what you meant? It's perfect. 2 more points. That's 4 total. Absolutely. Absolutely. 2 different styles. Choose which one you like. You'll see me go back and forth, so you kind of get used to the fact that either one works. It's perfect. But yeah. Please.
If we write it in the first one you did, should we keep it the same on both sides so it makes more sense, or does it matter? But
really doesn't matter. Yeah. So no, 2 for Jake. And I forget it. I can't remember if Jake's okay with you. I don't want to. Okay, you're good. Yeah, 2 for Jacob. I'll go back and forth as well. So 2 for Jacob. Yeah, notation's critical. You really do have to have the right notation. But to your question, they don't care. Like if I have a mix of those 2 styles, they won't care that because both are accepted. So, anybody else? Let's stop 3 for Jake. So 4 now. Okay. Next thing. So what we've done now is we've said, okay, I'm starting with the function f. My goal is to find a formula for the rate of change of f, the tangent slope of f, the f prime. This symbol right here means exactly the same thing as this symbol. So another point for Jake, there's another thing you can switch up, and they don't care. You can go from this style to this style to this style, no problem whatsoever. So just kind of your choice. You'll see me flipping back and forth pretty seamlessly, just kind of depending on how it feels at the moment. So, question. Okay, the other half, this right here is just a new algebraic expression. All I do is write it down. 2, 3x to the 4th, minus 5. Nothing special there. I just, 2 minus 1 is just 1, so I don't really write that. Now what I have is a lot of students think of the movie that came out a few years, well, it's actually been quite a few years now, Inception. Using the rules is like solving a problem within a problem. And that's how they always work. We wanted to find f prime. So what we did is we applied the derivative operator right here to the function f. That's what we're doing here. We're applying the derivative operator to the function f. Once we do that, we use the rule to create a new expression, but that new expression has a problem within the expression. Like the derivative operator is still there. The derivative operator is no longer present here. It's not operating on that. That part's done. But we still have a derivative operator here operating on this. That was a piece within f. That's why they think of the movie Inception. I used the derivative operator here to operate on all of f. Now I'm using the derivative operator to operate on something inside of f. And that's how it always works. Questions? Please do.
Did you use the derivative operator in the first part, or is it more that you split it up?
What I did is I looked at this function and I said, okay, this function f is absolutely some g of x being raised to a number. So that's a power rule situation. So I'm going to apply the derivative operator to the entire function f, all of it. It looks like we're splitting it up. We're really not. We're using the rule. The rule says that if you apply a derivative operator to this power function, this g of x to the n, that expression can be rewritten like this. So that's what we did here. We rewrote it, and the result of our rewriting was we end up having to apply the derivative operator to the element that was inside of f, the g of x that was inside of the f function. Does that answer your question?
Yeah.
Okay, please, John.
Could you, this probably is the wrong notation, but could you like put in one big equals chain then? Because they're all equal, or are they not all equal?
It is true that you could say this, 2 more for David, by the way. I gotta remember to give out more tickets because you're only here half as often, so anyway, so the ticket count's gotta go up. This is equal to this, and this is definitely equal to this. So yeah, you could write it as a big chain. Don't. It tends to lead to mistakes. So that's not a illegal thing to do, but it does fit into this category that I won't let you retake if you start doing that. Like, you have to go straight down the page. So I totally get that that means you'll use more paper. I am happy to buy you paper if you can't afford it. Like, I'm serious. Using a lot of paper will help you get a better test score. Trying to cram it in won't. Now, some people are very neat and tidy, and they can find ways to make it way smaller than I would make it. But just make sure you're going straight down the page. Some people have small enough handwriting that they have been able to go like one column and then a separate column, and that's okay as well. Just straight down the page, don't go across. More for Jonathan? Other questions? Oh, please, Brenda.
If a function is just to the power of like 1, can you still find the derivative of it?
Mm-hmm. You can still apply the rule, although if it's to the first power, we actually will use a different rule, and it makes it a little bit easier.
Oh.
So this rule still works. The power rule works if the power is to the first, but there's just an easier way. So I'll show that in a second. 3 total for Brinley. Anybody else? Please, Ben.
Do you have to continue writing the derivative of f notation on the left side of the equal sign, or can you drop that off eventually and just write the equal sign?
No, perfect question, Daniel. Because the left side of our equation sequence, as we go straight down the page, because the left side isn't changing, you are allowed to simply leave it blank and just put an equal. Absolutely. It's critical that from this line to this line you have something, though, because the very first line says f of x equals, the next line doesn't say f of x anymore, so make sure you do something there, but then subsequently you wouldn't have to. No, perfect. 3 total. I did this because I wanted to show you 3 different styles, and then you can use any of them. So, and I show you the 3 styles because they use 3 different styles. So you get used to seeing something they're giving you as a question, and you don't get confused. So, anybody else? Awesome. Okay, next step. Basically, like the movie Inception, I just start over. I need to say, well, I've got the derivative operator here. This derivative operator is being applied to this. So I need to find a rule that fits that situation. Brinley, another point, she saw a rule that did fit. The power rule does fit. But when the exponent here is 1, I don't like to use the power rule. Doesn't mean you can't, but I would highly recommend against it. There's just a better way. It's easier, quicker, faster. So even though the power rule would work, because this is some function to a number, I'm not going to use the power rule. Instead, I'm going to use this one down here, this add subtract rule. The add subtract rule looks kind of messy. It's really easy to remember. So I would not memorize the rule. I would just memorize the idea. I put the rule on your sheet for completeness, but I would just memorize the idea. The idea is very simple. If I've got a derivative operator, d dx, that is being applied simply to 2 terms that are being added, I can apply the derivative operator to each term separately. So I do the following. Let's pull this out of the way. Okay, let's see. This. So, I've got, now make sure you maintain the multiplication here. This is 2 multiplied by 3x to the 4th minus 5, multiplied by whatever this is. So that's going to break into 2 terms, so I've got to have a big parenthesis here. Don't forget the parenthesis. I'm going to have d over dx of 3x to the 4th. Now whether I subtract or add it doesn't really matter, it's kind of my choice. I'll put subtract is fine, d of 5 over dx. Like that. Questions or curiosity? Please.
Is the 3x to the 4 like times by the d, or is that the whole d over dx? Like is it that, or is it?
Got it. 3 points total for Jonathan. The d never stands alone. So it's never d times, it's d of. It looks like multiplication, it isn't, it's d of. It literally means the infinitesimal difference in 2 values of this thing. Like, you know, how different are 2 different values of this if the x's are really close to each other, divided by the infinitesimal difference of the actual 2 x's. So it's a big mouthful to say. You don't ever really have to remember that per se, but that's what it means. So no, the d can't separate. The d only applies to the 3x to the 4th. It does not, the dx is separate. You can write it like this, or you can write it like I did over there. Either way is fine. I don't know if I answered your question though. Okay. Anybody else? All right. Don't forget this parenthesis. It's a really common error. So if we can start today not forgetting those 2 parentheses, it will make a big difference. Notice how the inception thing happened again. We applied that add subtract rule, and we ended up with, now we have 2 more ddx operators. So it's like you just keep doing problems within the problem. If you pay attention, what you'll notice is you're working from the outside in. We started off by applying the derivative operator to all of this. After we applied the power rule, we ended up applying the derivative operator only to this. It's only bad about writing on the board so much you get a million circles. Switch the pen so I can get rid of some of them. Now we're applying the derivative operator to these 2 separately. Right here. That's how it will always work. You work from the outside in. Okay? Questions or curiosities? Questions have been really good. So, cool. So next line, as Daniel said, point for Daniel, there's 2. I really don't have to write anything on the left. I can just put an equal sign. That's totally legal. I'm going to write f prime again just because it's our first one. I don't want us to forget that that's f prime. This part, there's no derivative operators. There's nothing for me to do other than rewrite. Don't do this. That's your code for I don't ever want to retake a test again. I'm serious. Don't do that. Okay? It's not legal to just do the ditto marks. You must write 2, 3x to the 4th, subtract 5, parenthesis. We have a new rule. We've got this one now we're going to use. So you can start to see now the value of the pink sheet and why you'll need to get it memorized. I've got this situation, this multiplying constant rule. I've got 3 is a multiplying constant, and here's a power function, x to the 4th. So I've got 3 multiplied by something. Notice in the rules, f doesn't coincide with the f here. Don't get them mixed up. It's just a representative of some function. So I've got 3 multiplied by x to the 4th. The rule says that can become 3 multiplied by d dx of just the function itself. So it's a lot of writing as we're starting to learn these rules, but eventually we'll write a lot less because we can do a lot more in our head. But what we do is we pull out the 3. You're left with d over dx of just x to the 4th. Like that. We'll worry about this piece here in a second. So, questions or curiosities about anything? Please.
So can you not multiply out the 2 times 3x to the 4 times 5?
Oh, 3-point for Logan. You can. You just don't want to. So there's nothing illegal about multiplying these out. I've just learned by experience that I don't need to, they don't expect me to, and so no reason. Yeah, that's all. Yeah. One more for Logan, total of 4. Question. Please, Brenda.
These x's aren't like representing the same thing, right? The x to the 4th and the x on the bottom.
Oh, good question. They actually are.
Oh.
Yeah, in kind of a way that's a little hard to see, but they really are. What we start with, see if this helps. Really good question. What we start with is a formula where we could plug in an x. I gotta reset this. This is getting crazy. Just keep circling that thing over and over again. We start with this formula, and the x is just a placeholder. It's just saying plug in any number you want and find the y coordinate. Make sense? What this means here when we're finding a derivative is what we're really trying to do is literally plug in an x of, say, 4, and then an x of 4 point tiny bit, as well as x 4 point slightly less. And we're trying to say, well, when we compare what's happening at this x with what's happening at this x, well, what's the y doing? We're literally finding a slope. Yeah, so the x is the same x,
Okay. It's
just being
function
used.
of-
Does that make sense?
Yeah.
Perfect, 4 points. Okay, I got to do something with this. And this fits Brinley's question, another point there, perfectly. D means difference. We're trying to find out how much does 5 change compared to how much x changes. But 5 isn't going to change. Like, look over here. In this formula, like I just said to Brinley, if I were using these 2 different x's or these 3 different x's, I would be getting different y values here. They'd be very close because I'm using such small changes in x, but they would be different. There's no x to plug in here. 5 is 5. It's not going to change. So the change in 5 compared to the change in x is always going to be 0, because 5 isn't changing. Whereas here, as I plug in these different x's, I absolutely observe a change in this compared to the change in this. That's a tangent slope. Over here, 0. Another way to look at it is the function 5 is a function that would look like this. Like, this is what a function y equal 5 looks like. It's just a horizontal line. As we are finding derivatives, we're finding tangent slopes. The tangent slope of a horizontal line is 0. So the derivative of 5 is 0. Reminder, d doesn't mean derivative, d means difference. Derivative is the comparison, the change in the y compared to the change in the x. So derivative is the entire box, d just means difference, not derivative. So. Question? Awesome. All right, so 0 here. We still have a derivative operator here, but that now fits the rule we used in the beginning. It fits the power rule of way up here. Because my g of x is now just x, my n is 4. You need me to talk through that in more detail. So I go back and I apply that derivative operator, and I write f prime. And you don't have to write that, another point for Daniel. Another point for Logan, don't multiply these out. Just leave them alone. Everything is being multiplied here, so don't get mixed up. That 3 is still a multiplier. Now I'm going to apply the rule. So I bring down the 4. And I have the x. New exponent will be 4 subtract 1. Then I would have d over dx of just x. I simply apply, there's no minus 0 anymore. You don't have to write that. I simply applied the power rule. My n was 4. My g of x was x. Here's my 4 minus 1. Now I've got d over dx of just the x. Questions? Jacob, please.
Okay, so all you're doing was applying the power rule to the second part of the equation, right?
To just this little piece right here.
Okay.
Yeah, and it's that whole idea we start on the outside, we work our way in. I think of it somewhat like, wait, if you've heard of the old game Pac-Man, most people have. Yeah, it reminds me of that kind of like we're eating outside in. And so the first time we apply the derivative operator, we all, listen to this for sure. The first time you always, no exceptions, you apply the derivative operator to everything once. The entire piece, all of it. Then you start, as you apply the rules, it will just happen. You don't have to even think about it. The rule will kind of migrate through the piece. Like the operator applied to everything, then it applied to this, then it applied to this and this separately, then we were able to split these two, and now we're just operating on just the x to the 4th. It just works its way through the problem automatically. You don't have to even think about it. Please, John.
Where did you get that coefficient 4x on the bottom? Where's the 4 come from?
So right here, I had d over dx, the derivative operator, applied to x to the 4th. So I looked up and said, that's the power rule that I'm going to use. The g in this case is x. Remember, as we use the rules, the meaning of g will change. So this is x to the 4th. So the rule says that expression is equal to 4. That's where the 4 comes from. You see it?
The exponent.
Right. The exponent here becomes this. Then there's my g. That's the x. New exponent of 4 minus 1. You see that? Okay, question?
Yeah, so there will always be the coefficient, and then the exponent minus 1 will always be the same number in this situation.
Yes, when you're using the power rule. We'll learn some other rules, but that's where we're starting. It's perfect. 3 more for Jonathan. Anybody else? Cool. We're basically done because, back to Brindley, another point there, this means the difference in x divided by the difference in x. But we've talked all year about how something divided by itself is always 1. So dx over dx is 1. That's kind of like a stop sign in a sense. That's like telling you you're done. Like when there's no other derivative operator in the expression, that means it's worked its way through the entire function. So we're finished. The last thing to write would be the final result, which would be this, f prime of x. Now, another point for Logan, you can say, well, there's a 2 multiplied by this, multiplied by 3, multiplied by 4, multiplied by x cubed. The order of multiplication is irrelevant. So I kind of go with what's a typical habit, which is they'll say 2 times 3 is 6 times 4 is 24. And I've got an x to the 3rd, parenthesis, 3x to the 4th, subtract 5. And what we have created, don't forget what we have created. We started with a formula that can be used to find a list of xy pairs. We have a new formula that can also find a list of xy pairs. But every one of these y values is going to represent a tangent slope of this. That's what we've created. In Unit 1, we never did that. I did it for you. Like in Unit 1, I showed you these graphs. Let me open up a file here. In Unit 1, we saw these graphs a lot. Let's go here. these formulas were created using that process I just showed you. So I gave you the formula for f, and then I created the formula. Well, actually let the computer do it for me, but created the formula for f prime. Then I did it again to create the formula for f double prime using the process we just went through. This one. Question? Oh, please, Brenda.
Sorry, wouldn't it be x to the 4th minus 5, like 3?
Oh, thank you. How many saw the mistake? 2 points, 3 for Brindley. Yeah, I just missed. That's just an error. Sorry about that.
Okay.
Anybody else? Awesome. Let's do another example. Okay, so let's look at. Okay, the good news is that if you understand the process, applying new rules isn't really hard. It's just the exact same process, just different rules. So let's do one that's a little different here. Let's use the square root one real fast. So write that down. Y equals root 3x squared plus 1. And we do the exact same thing. We apply the derivative operator to both halves of the equation. So we get dy dx equals d of square root 3x squared plus 1. Question? Cool. We go looking for a rule. In this case, the power rule kind of fits because this is something to a power, and this really is 3x squared plus 1 to the 1/2 power. So the power rule really would work. However, I prefer to use the square root rule. It just makes the final result a little easier to obtain. So both of them work. It's actually unusual. Most of the time only one rule works. So next line, this is dy dx. Or the point for Daniel, you can just leave it blank if you want. So the rule says this can be rewritten like this. So I just copy it down. 1/2 square root. The g of x in this case is the 3x squared plus 1. Now I've got d over dx of that g of x. If you notice, many of the rules end in exactly the same way, with the d over dx of the g of x. That's because I did something that most teachers don't do. I took the rules that are typically taught and then I honestly made them better. Yeah, sorry, big ego there. I did. They're better. Like I combined them with what's known as the chain rule. We won't worry about learning the chain rule quite yet. It was right here on your list. But basically, I've taken the simple rules that you would find in a textbook. Like you won't find my rules in a textbook or online. They're like my version. Okay? But they're better. Sorry, don't say that with any humility. I'm using the chain rule in conjunction with the power rule that I found in a textbook. And I put them together to make my power rule much better. My square root rule much better, promise. But they all have this thing on the end, and that's because of how I combined the two rules. You don't need to worry about it right now. As we get better and better, you'll start to see what I did. But just be aware that that's why they all end that same way. Questions to hear? Please.
Both like I've already said this, but how do you know that g of x is 3x squared plus 1 instead of just like 3x squared or just?
Gotcha. It's simply me identifying a match. That's all I'm doing, just trying to find something that matches perfectly. And what I found was, in this rule, if I choose, so it's my choice, if I choose to think of g of x as 3x squared plus 1, now it matches the rule perfectly. Because the rule says square root of some function. See what I'm saying?
Yeah.
3 points. Perfect. Yeah, it's just a matter of making sure it matches. Yeah. Cool. So next line equals this piece, nothing to do, just write it down. Oh, another point for Logan. Make sure you don't make the mistake. With the root, you can't distribute. So that would not be legal to distribute the 2. Previously, we could have, we just don't want to. But okay, just like before, I use another rule. So that's the add subtract rule. So I'm going to split that into a parenthesis d of 3x squared divided by dx plus d of 1 over dx. A lot of the problems will start to feel similar. They'll feel like you do a different rule to begin, and once you begin, the subsequent steps become somewhat identical. That's pretty common, actually. That's why getting good at this goes pretty fast. Questions there? Cool. Next line. Again, no ditto marks, just write it down. Parenthesis. We already know that this is going to be 0 because that's d over, 1 isn't changing. We're going to pull out the 3. That leaves dx squared over dx. I do not have to write plus 0. You can do that part in your head. That's fine. So, question. Again, make sure you write what I write. It will only take a couple of homework assignments before I will give you permission to start skipping a lot. Because as you get good at this, you can do a lot of it in your head much quicker. But just start out writing everything. It helps you learn the rules. I know it's a little tedious, but it really will help in the long run. Square root 3x squared plus 1. Don't forget the parenthesis. There's a 3. For the parenthesis, now we're using the power like we did before, so bring down the 2. There's my x. 2 subtract 1. I'm left with dx over dx. Don't forget to write the dx over the dx. As long as you're doing that, you'll remember why we have to, and it will help in future problems. Questions or curiosities? Please. Okay.
So you said before, don't do equal signs like vertically with 9, or is that fine? Just leave off the F9.
Oh, on the left side?
Yeah.
Yeah, this you can leave blank because they're the same.
Okay.
Yeah, that's legal. They don't mind that. What they don't like is the idea of doing like a ditto mark for part of it. But that part is legal. Perfect. 3 points. Okay. We're pretty much done. Just kind of put it all together because remember this is equal to 1. So we end up with, now I'm going to cheat a little bit because I've run out of board space, but your paper keeps going. So I end up with dy dx equals, remember, you have a fraction. This is 3 over 1. This is 2x over 1. So fractions multiply across. They'll notice that this factor in the denominator will divide with this factor. So you'll end up with 3x on the top. On the bottom, square root 3x squared plus 1. For the homework, the answers are on the back, so you can check as you go. So, question? Brilliantly, please.
So that x 2 to the line minus 1, like the dx over dx, so it would be just the 2?
Let me say it back to you. So you're okay that we have these 3 things?
Oh, wait.
Do you see it now?
Yeah.
So you're okay?
Yeah.
3 points for asking. Anybody else? Please, Jake.
Can we write, so you asked the question earlier, but can you do the dy over dx as f prime of x when you write it on the form?
Oh,
Does that make
gotcha.
sense?
Technically, no. Just because they did not declare this function to be f of x. So there really is no f in this particular problem.
So we have to leave it as y.
It's better to leave it as y. If you want, on the AP test, you literally could do this. You could say f of x equals, like you just tell them that you're going to assign f to this formula, and then it's legal. So that's okay if you do that, but you do have to write that first. 3 point.
Although when you have to put y prime, if you're saying y equals, then
Well, I think what you're saying, Jonathan, is I could do that, Jacob, Jonathan together, and 3 points for each of them. dy dx means y prime. So you could write this. That would be legal. And that's probably a good one to use once in a while because they'll do it. They'll use that notation. Yeah. They'll do this as well. They'll say, well, y is really a function of x. So instead of writing, f of x and then f prime, they go with this one. They go, well, the formula is y equals, so now we have y prime of x equals. This is kind of uncommon, but it is legal. So, question? Awesome. Okay, we're getting really close. The bell's going to ring in like 20 seconds. The homework is problems only 1 through 20. Please do not do more. I think beyond that, honestly, beyond that becomes busy work. Yeah, no, I put a lot of problems just because I found it in a, it's easy to find. And it gives me a lot of different examples I can show you. But don't do more than 1 through 20. Also, look on Canvas. I will have many examples posted of, like the low, I won't do the, there'll be a lot of examples posted if you want to get more help or reference that sort of thing. Good work. Don't forget the test.
Yes.
Don't forget the test. Good job, you guys.
Let's let it go right now.